espero un día que puedo hablar solamente en español en este seminario, pero hoy no es el día. Falto el vocabulario y el fluyo. Entonces, I'm going to have to give this talk in English, I'm afraid. So apologies about that. Okay, so this is a talk that's related to equivariant topology. So topological spaces with a group action on them. And I want to start by just talking a little bit about what the cohomology that we're going to use to look at these spaces is like. So if you recall that cohomology is a contravariant functor, you can always map a point to a space, which means that, I'm sorry, this first one's backwards. This should be, you can always map a space to a point. And so contravariantly, you have a map from the cohomology of a point to the cohomology of a space. And so in general, in any cohomology theory, the cohomology is a module over the cohomology of a point. So the cohomology of a point is always an important part of the theory. However, in the theory we're about to discuss, the cohomology of a point is actually already quite complicated, which you might not expect. So let me build up to why that is. So the group I'm interested in is just C2, the group of two elements. Couldn't be any simpler. There are two irreducible representations of that group. And I want to write RPQ for a general p-dimensional representation where q of those dimensions are signed representations, where the action of C2 is to just switch the coordinates to multiply by negative 1. So if you think about the two-dimensional possibilities, R22 is going to be a plane where you're switching both coordinates, and you can think of that as just rotating the plane. And if we compactify, that's what this little hat means, that plane, we get, gather up the point at infinity to a point, we get a sphere that's rotating. So S22 is the compactification of this two-dimensional representation with two sign representations in it, and it's this rotating sphere. S21, we have just a reflection that we've compactified, and so we get a sphere that's reflecting across an equator. And of course, there's R20, where neither of the representations is sign representation. So this is a trivial representation, and we have a sphere that has no action. So I'm using red here to denote fixed points, things that aren't moving when we act by the group. So these are called representation spheres. And if we're doing topology where we have, if I tell you I'm thinking of the two-dimensional sphere and I have three possibilities for what I'm talking about, well, we have more spheres, and that means we have more suspensions. So in vanilla, by which I mean non-equivariant topology, in vanilla topology, if you smash a space with a sphere, you have this index shift. You're subtracting a number from the dimension of the homology or the cohomology. Now we have more spheres we can smash with. And that means if I want an analogous procedure, smashing a space with one of these representation spheres should mean that I'm subtracting not a number like before. You guys can see my cursor, right? Can you see? Okay. But we're rather subtracting a representation. So the values that we're putting on this cohomology theory aren't numbers. They're representations. And so that's why this is called an ROC2 graded theory. The theory is graded not by numbers, but by representations of the group. Okay. And because our group has sort of two dimensions of representations, the trivial representation and the sign representation, we're going to just make this a bi-graded theory. We'll have a P and a Q that indicate which representation we're talking about. Okay, so I said the cohomology of a point was complicated. You might expect the cohomology of a point to look like this. Okay, I have a p-axis and a q-axis, but it's a point. So it should be boring. It should just be one copy of F2 if we're working in F2 coefficients. However, that's not the case. There's something in degree 0,1 called tau. There's something in degree 1,1. It's called rho in the literature. And this is a ring. So I can multiply these elements by each other and I get an entire infinite two variable polynomial ring up here. And it doesn't stop there. There's also an element in degree 0, -2 called theta. That element is divisible by rho and tau in the sense that there are elements below it, which when you multiply by rho or tau, you get up to theta. And in fact, it's infinitely divisible. So this is a non-Noetherian ring. It's a pretty ugly ring to work with, honestly. And it's often easier to just represent it with these two. We call this the upper cone and the lower cone to represent the whole ring. Okay, so let's start playing with computations in this theory where we're working with modules over this ring that we called M2. Oh, is it being weird? Okay, so this is three-dimensional space with one sign representation. We're rotating around the z-axis. And if you imagine taking projective space in this three-dimensional space, so the space of lines through the origin in R3, you might recall this gluing diagram is a way of representing projective space. You can fold up a circle to make RP2 in this way. Most lines that I rotate across the z-axis are going to move to a different line. The exceptions are the z-axis will rotate about itself, and it's fixed, so that's why it's colored in red. But also any line that lies in the xy plane is going to rotate 180 degrees, and if you rotate a line by 180 degrees, it's going to be the same line. So that's a circle that's fixed as well. So what's this space called RP2 twist has this action, and we can represent it by taking the gluing diagram of RP2, giving it a reflection action. So this is a circle here. And most points on the boundary are sent somewhere else, but because of the identifications of this gluing diagram, this point is sent to itself. So that's another fixed point. Okay, so that's a circle that doesn't look like a circle, and one point that looks like 2 points. All right. So I want to calculate the cohomology of this thing. And I can build a 0 skeleton, a 1 skeleton, and a 2 skeleton by taking a point, making this circle that has this reflection action on it, and then attaching in a disk that has this other reflection action on it. If I quotient, I've got this circle around the outside, and if I quotient the space by the circle, I'm folding it up to get a sphere with a reflecting hemisphere, or a reflecting equator. Okay, so I'm getting these two nice spheres. So to build a spectral sequence from this filtration, I have these ingredients that I'm going to try to recover the cohomology of the original space. I need to start a spectral sequence that has as its E1 page the quotients of the various n skeleta by the lower dimensional skeleta. So in this case, that's going to be a point. We've talked about the cohomology of a point already. The cohomology of S11, which is going to be a suspension of a point. So it's going to shift up and to the right by 1. So there's another copy of that thing. And then of S21. Now, I happen to know that this spectral sequence collapses. So what we're looking at here is actually the answer. The cohomology of this equivariant space is just a copy of M2, the cohomology of a point, and 2 shifted copies of M2. Okay, that was sort of easy because nothing interesting happened. We just built the space and figured out what its components were. Let me do this again. I'm going to talk about the same space in another way. So now I'm going to take the gluing diagram for RP2, but instead of reflecting it, I'm going to rotate it by 180 degrees. Well, the point in the center of this disk is going to be fixed, so that's not moving when I rotate 180 degrees. But now, if you take this point and you rotate it 180 degrees around the circle, you're back where you started because of the identifications. And so, in fact, the entire outside of this is fixed. What that means now is if I quotient, my 1 skeleton is a trivial circle, a circle that's not moving at all. And when I quotient by that trivial circle, I'm getting a sphere that's rotating and has only a north and south pole fixed. So I'm getting an S22. So now when I build the spectral sequence for this thing, And I'm going to leave the point out. It just gets too crowded. So I'm just going to talk about how these two pieces interact. I have a 1-0 suspension and a 2-2 suspension. And there's an actual differential here. Now, we already know what the answer is supposed to be, right? On the previous example, we calculated this cohomology. So somehow I need this spectral sequence to converge to the same thing. But how? Well, let me look at these rings in a little bit more of the complexity that they actually have. So they're made of all of these copies. And what I want to do for running this spectral sequence is look at the kernel and the co-kernel of this map. Well, this blue dot goes to this blue dot, but if you multiply up by the element that we called tau, there's nothing purple to hit here. And so this is going to be in the kernel of the map. And in fact, everything above it, because this is a ring map and it's tau times something that's sent to 0, that's also going to be sent to 0. The lower cone, similarly, for ring reasons, it has to go to 0. So the kernel of this map is almost everything, except for this one blue dot. Well, if only one thing is mapped across by the differential, then the co-kernel is everything that isn't hit. It's all of these other purple dots. So I have this other co-kernel. Okay, so on the second page of my spectral sequence, I have these green. Let me toggle back and forth. Sorry, let me. There we go. I have these green dots that I'm going to draw more simply. I have these orange dots. And this is the second page of this spectral sequence. Now, there are no other non-zero differentials. That's the end. So this is also the E infinity page of the spectral sequence. And if you kind of squint your eyes at these shapes, you can see sort of an upper cone here with a lower cone below it, and another one over here. Well, there's a theorem that says that this is in fact the case. We're going to get the cohomology that we got before, but it's a much more complicated story to get there in this situation. So Cron-Holmes theorem says this happens in general. If you have a space that's finite type, which is pretty generic condition for a space that you might want to build, and it's built out of rep C2 cells, then you're going to get a free module, which means when you have differentials like the one before that breaks your cohomology up into something that doesn't look like just a bunch of copies of M2, actually it is just a bunch of copies of M2. And what happened here, if you look at just sort of the generators of what we started with, when there was this differential that they made them interact, they moved. And we ended up with one moving up and one moving down. This is called a Cron-Holmes shift. And these Cron-Holmes shifts preserve topological dimension. If things move up and down, their topological dimension along this p-axis doesn't change. But it also preserves what's called the fixed set dimension. P minus Q measures sort of in any one of these representation spheres, the things that aren't moving, the fixed smaller dimensional sphere. And that's not changing. If this guy leaves this orange diagonal, this one comes and takes his place. Okay. So in general, if I'm calculating a more interesting spaces cohomology than just this RP2, I don't know the differentials. I can build the spectral sequence, but I don't know if this piece has a non-zero differential mapping to that piece or not. What I can do is write down all of the possibilities and get, well, maybe there's a differential and I get this cohomology for the 2 skeleton. Or maybe it's this cohomology for the 2 skeleton. I attach the next cell, maybe this happens, maybe this happens, maybe this happens, or maybe we're over in this other case, in which case something else happens. You can build all the possibilities. One of the things that I come to here will be the real cohomology of the space, but it's not clear which one is the right answer. So the question I want to answer for today's talk, and this is an extension of things I did for my PhD thesis, which was to calculate things in multiple ways, like I just showed you with this simple example, and play the different calculations off of each other, is there a way to quickly determine, if I give you 2 M2 modules, that one can actually be a Cron-Holmes shift of another? In other words, if I give you this module and this module, can you figure out how I got there? Or even that I can get there through these Cron-Holmes shifts? So to do this, I'm going to need to start by generalizing the idea of the Poincare polynomial. So the vanilla Poincare polynomial, the one you might be familiar with, says you can make, if you take a space and you take its cohomology, you can look at the rank of each dimension of the cohomology and make that the coefficient of x to the I for that power, and add those up, and you get a nice polynomial that tells you the information of the free rank of the cohomology of the space. Well, now I need something fancier because my theory is bigraded. So I've got a fancier p that I typeset here, and I need two variables to represent this information as a polynomial. This new fancier Poincare polynomial plays well with the forgetful functor. So we've got a forgetful functor. If you give me an equivariant space, I can just forget that there's any group action and just leave it as a space with no action at all. And if I do that and then look at its Poincare polynomial in the vanilla sense, that's the same as taking this fancier polynomial and then just evaluating at one. This is sort of dropping down the higher axis and ignoring any of those y's. There's also a fixed set functor. So if you give me a topological space with a group action, I can look at the points that don't move. That's going to make a subspace which has no action. And so this is another functor from equivariant spaces to non-equivariant spaces. And again, this plays nicely with these two different kinds of Poincare polynomials. To get the p minus q, this fixed set dimension we saw before, you have to simply divide by your q direction. So you evaluate your polynomial at x and x inverse. Okay, so for example, we saw this shift before, where this guy comes up and this guy comes down to put us here. Here's our fancy Poincare polynomial for this situation. Here's the Poincare polynomial there, right? This point is 1, 2 in the x direction and 1 in the y direction. So I have this x squared y. This point corresponds to this term, and this is 0, 0. So that's x to the 0, y to the 0. If you plug in y equals 1, you get the same thing. And if you plug in x inverse, you get, well, the same thing. So this is maybe an argument that we do need this bigraded theory. What's happening in the shadow of this theory in the non-equivariant world doesn't know that any of this is going on. The Poincare polynomial is blind to these phenomena, the old Poincare polynomial. Okay. So I'm interested in Cronholm shifts. I'm interested in the ways that these generators can move when we have non-zero differentials in the spectral sequence. And I want to define KNS to be the difference in the Poincare polynomials when we have an M2 moving up by some shift S, and doing that by mapping to an M2 that's moving down by that same shift S. And I claim this is going to be the general formula for that. So here's an example. If this point shifts up and that point shifts down, I'm changing from a 1 and an x to the third y to the fifth to a y squared x to the third y to the third. The difference between these two things can be rewritten. In this example, I'm not shifting up an M2, I'm shifting up this thing here, which means that I've taken a story that could have started at the origin and I've moved it to the right. And if you look at the algebra here, what you get is that, yeah, this is like a K11. It's a shift up by 1 to something that's over 1, but it's been shifted to the right. So that's where we're getting this x here. So basically, I want to take these KNSs, and to quantify all of the possible Cronholm shifts that can happen, I need to be able to multiply them by arbitrary elements of the polynomial ring, x's and y's. Well, this is an ideal of the ring. So I'm going to call the Cronholm ideal the ideal generated by all of these KNS shifts. I claim that this is going to actually be kernel of the two functors I described before, the fixed set kernel and the kernel of the forgetful map. And another sort of way to say that is that K is going to be principally generated by the simplest Cron-Holm shift to the K11. Okay, so let me sort of sketch why that's true. So first of all, if you have a K1S, a shift by S from two adjacent dimensions, we can rewrite that as K11 times this polynomial. So sort of a proof by example here, but if I want to shift this point up by 3 by having a differential to the lower cone of this thing, which shifts it down by 3, my polynomial is going to be given by this expression. But what I can do instead is map from here to here, shifting this one up and that one down, which puts me in this situation. And then do it again, map from here to here, which shifts this one up and this one down to here. And then this one to this one again. This comes up, that comes down, and I'm here. And you see that this ends me at the same place. This has the same result. And this is a sum of a K11 shifted up by 1, and a K11 shifted up by 2. So multiplying by y squared. Okay, and the algebra works out nicely that yes, indeed, this is the same thing as K13. Okay, and this is going to work in general. So K1s is going to be K11 times this polynomial of y's shifting up. On the other hand, if you want to do a generic shift, KNS, you can get this by multiplying K1s by the appropriate polynomial. So, okay, let's say I want to shift this guy up by 1 and shift that one down by 1. I'm going to use these intermediate steps as sort of a ladder. I'm first going to map, oh yeah, sorry, so that'll have this result. But I'm first going to map this one onto that one, shifting him up and him down. Boop. And this one onto that one, which is going to shift him up and him down. And then this one onto that one. Okay, so we see that has the same end result. And that's giving me this one, where n equals 3 and s equals 1. But the same sort of principle applies generally. I like this a lot because as an algebraic topologist, I like topology. And I do algebra because it helps me with the topology. And sometimes all of the shapes and spaces and visualization goes away. And I like this bigraded theory a lot because there's still pictures, even though I'm doing algebra. Okay, so we can now see if I can write KNS in this way, and I can write K1S in that way, then in fact, every Cron-Holm shift is some multiple of K11. And if I use the theorem that my Calc 2 students know about power series, then I can, or geometric series, then I can rewrite this as the expression we had before. Okay, so we can now return to this original question. We've shown that the Cron-Holm ideal is finitely generated. If I want to check in my theory if you can actually shift one cohomology into another by Cron-Holm shifts, how do I know if that's possible? Well, I just need to check if the difference in their Poincare polynomials is divisible by this thing, in which case it's in the Cron-Holm ideal, and it has to have all positive coefficients, right? The problem with an ideal is, of course, you can multiply by -1, and I don't want to say one shifted to the other, which means the other can shift to the one. It has to be going forward in time in some sense. Okay, I think actually that went faster than I thought it would. So that's my main idea. Since I have a little bit of time, maybe I can tell you why I'm interested in this. Maybe I should pause. Are there any questions based on what I've said so far?
Yes, of course. Bueno, ¿tienen alguna pregunta para él?
¿Alguien tiene preguntas?
No, yes, I got a question for you, Eric. You said at the beginning, can you go over back to your slide where you split over sort of homology group that you You were not sure that one. No, 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 you passed that. Two more south. No, no, two more front. That one. Yeah. No, the other one. That one.
There's a lag.
No.
It was taking a second. Okay.
No, no, no. Just wondering. So you say on that slide that you don't know what is your differential. I hope you're pointing toward this square 0. So to define your long exact sequence. So my general question is, what is the main struggle you find over the theory that doesn't allow you to define your differential?
The main problem is, I'm trying to take what I know about non-equivariant topology and bring it into the equivariant world where there's a group action. And the spaces I'm interested in mostly have no differentials. So I've been working mostly with Grassmannians. And if you're working over
Okay.
2, the differentials are multiples of 2, and so there's nothing. So if you ask the sort of existing knowledge about the differentials, the answer is they're all 0. But they're not 0 necessarily in this context. So if we look at this differential right here, forgetfully, if I can annotate, if I look at what we see in the non-equivariant, the traditional setting, there's an element here, and this element maps down to 0. So this differential is a 0 differential in the normal theory, right? If you're building RP2 and you're trying to calculate its cohomology, there's no differential. So the only reason I know this is here is because I know what the answer had to be from another calculation, and it couldn't just stay the way it is. It had to change. And so the technique that I'm using is this idea of building too many copies.
Okay, so.
And if I get a bunch of these possibilities, and then I build the space another way, I can make another one of these trees with a bunch of new possibilities, and then I look for matches. If this list has only 2 things in common with this list,
okay, yeah.
Then I've narrowed it down. It's one of those 2. And then I build it another way and I see if I can narrow it down that way. So I was able to actually get some answers doing this, but the problem is, I wrote a computer program and it's slow. I'm not a computer programmer, but there's also just sort of an exponential growth as you move forward in this tree. And so I think even if I was a really good computer programmer, I can't expect to make this very fast unless I can check very easily.
Okay. My next question would be, so these are cohomology groups, right? Cohomology.
Mhm.
What would be the counterpart groups to the homology group of the theory you are developing?
Yeah, so at least working in F2, where we don't have to worry about extensions as much, essentially you're just turning it upside down. So when we switch from cohomology to homology, I should be bi-grading this. One thing is we lose the ring structure. This is a ring. This is just going to be a collection of groups, but it's essentially just going to turn things upside down. So this is going to turn into this. It's just flipping.
Okay. So, I mean, excuse me, because it's been a while with us turning this. So basically no difference between the homology and the cohomology. Is that what you're trying to say, or I missed something?
No real meaningful difference.
Okay.
This reflection, changes the values of certain bi degrees, but I'm not aware of any reason you would be interested in homology that you couldn't get from cohomology.
So if you're working with cohomology specifically, I mean, if there is no answer, that's okay. We're just wondering, do you have the round theorem, or maybe you think it could be possible to have the round theory whenever at some point in the future you find the differential that would be possible to define the rank homology for the theory, or is something that you haven't thought about?
I have not thought about it.
Okay.
I feel like I have heard the expression equivariant de Rham
An
cohomology.
equivariant round theorem. Okay.
I think somebody does that, but I don't know anything about it.
Yeah, because if you find that the RAM equivalent version to this homology theory you're developing, maybe if the RAM theorem exists, maybe you can think in something further like Furubini theorem or something like this with Grossmanian you were working with it. So I don't know, just giving you dummy ideas that just.
Oh, that's an interesting. It's a very young theory. Like we're just now
Yeah,
getting
of course.
the idea of Poincaré duality. A paper was published, I guess, a year ago now. That's figuring out how Poincaré duality works in this theory.
So Poincaré holds for the theory.
Yes.
Okay, that's good. That's
At least for nice spaces. I think there are spaces that it doesn't hold for. But
okay, and finally, my last question to give the other from the audience to ask something if they have. If you finally find your cohomology theory on those interested spaces, would they have an equivalent manifold versions? I mean, 3D, 4D, or manifold-ish version of this cohomology theory?
yeah, so what I've actually had this work on mostly, I was talking about, is the Grossmanians.
Oh, that's right. Okay, cool.
There's an example of this is if you're building an equivariant Grossmanian. So I'm going to talk about two planes in 5-dimensional space. Well, if the 5-dimensional space has 2 sign dimensions here or 2 sign dimensions there, it's the same space, right? There's a nice way to map between these two things that's a continuous equivariant bijection. They're the same space. But if I want to take, so this is using the Schubert cell construction, where you can break up families of spaces into ranks of matrices. So let me just look at one of these. This would be like the ranks, or sorry, the row spaces. Row space of every matrix that looks like something here and something here, and then a 1 that clears out this column, and then something, oops, Y and Z here and here. Okay, so you can break two planes into ranks of different matrices that are set in this row echelon form. And now if I'm over here, so that these are trivial representation dimensions, and these 2 dimensions have a sign action, then the group action takes this to the row space of, well, these 3 columns don't change. Same, same, same. But now these are reversed. Well, this isn't in row echelon form anymore. This is supposed to be a positive 1. And so I multiply this column by, or this row by -1 to put it in row echelon form. And that's the row space of Wx0. Puts a minus sign here and here, makes that positive. Okay, that was supposed to be a 1. So that's why there's a
okay, I think I got it. I think.
Oh wait, I just got confused because I thought I was going to have a minus here and a plus there.
Yeah, there is a mismatching over there. Well, never mind. Okay.
Something like that. You can put it in different ways.
Yeah.
And then if I put the minus sign somewhere else, I get a different way of building it.
Sure.
And we already kind of saw a piece of this in my example from the beginning. That's RP2, right? RP2 lives inside of the Grassmannian. That's the other RP2. This one came from point a 1-1 cell, a 2-1 cell. And this one, we have a trivial. So I've got a point, something in dimension 0, 1, 0, and then something in 2, 2. So these are two different ways of building the same space here, where this one has to shift up and this one has to shift down. When I build these two spaces, these two different ways, let me clear up my mess. We get two different starting pages with very different things that have to convert to the same ending place. And neither of these is the answer. Both of these have Cronholm shifts that come to a third place. So what I've been able to figure out so far, Cronholm in 2009 came up with all of the projective spaces. My thesis advisor, Dan Duggar at University of Oregon, actually did the infinite version of this in 2012. And then I was able to figure out the GR2s where there are two.
Some finite dimensional version of your advisor, basically.
Yeah. And the funny thing is that the finite dimensional version requires the infinite dimensional version. Usually you start finite and you build up to infinite.
Exactly.
I came from the top down. Yeah. And then also these guys. So that's all that's known right now. So for example, I'm trying currently to write a program that will use this Cronholm ideal to figure out the next thing that I don't know, which is just GR3, R63. It's just a little 9-dimensional manifold with an action by C2, and we don't know its cohomology. So.
Good. Well, thank you. I don't have any more questions. ¿Alguien más tiene preguntas para Eric? Well, bueno, Eric, vamos a cerrar en español ya que entiendes un poco. De verdad, muchas gracias por aceptar la invitación al seminario. En lo personal me agradó bastante tu charla. Es bueno recordar cosas que se vieron hace un tiempo atrás. Muchas gracias, de verdad, gracias por venir y bueno.
Gracias.
Y bueno, de verdad que muy bien, muy bien. Gracias por todo. Bueno, voy a detener la grabación.